Howdy. Today we'll be starting electrostatics. Before we can really get into the unit, we need to go ahead and review how to convert between different units, and specifically we need to know prefixes. Okay, so here's a list of the prefixes, and so I put a document on the assignment. So if you go to the electricity assignment 1, you can see this picture. You can also just Google. I looked at like physics prefixes and this came up. And so, but I put it on a PDF for you that if you wanted to print out, you can have it. And it's going to be really good because we're going to be using a lot of prefixes. It turns out this unit, we have a lot of really small numbers. We're going to be dealing with a lot of things down here. Okay. And so we need to be able to convert between these and the base units. Okay. So base would be in between. It's just 10 to the power 0. It just doesn't have a prefix. So we'll do one practice real quick. Otherwise, if you need more practice, I mean, this is something we're supposed to have learned in chemistry and other courses beforehand, and it's something we reviewed at the beginning of the year. And so at this point, I just want to review it real quick because we haven't been doing as much of it, but we need to use it this unit. So let's try one. Convert 9.1 micrograms to kilograms. So there's a bunch of different ways you can think about this. Here's how I'll do it. I'm going to first write micrograms, and we write it like this. If you're unsure, you can look at your... Hold on 1 second. If you're unsure, you can look at the sheet, and you can look for the prefix micro, and then you can look for the symbol, and it has the symbol mu. So mu is also the coefficient of friction, but when we're talking about on a unit, it means micro. This is equivalent to 9.1 times 10 to the negative 6 grams. How do I know that? Well, if you look on that sheet, it says micro is 10 to the negative 6. And so what that's referencing is referencing the base. And so we can immediately convert micrograms to grams. And that's the first step. Really convert everything to your base first. So that's the easy step. Just use the sheet to, by definition, what micro means. It means 10 to the power negative 6. Okay. So now that I know that number is 9.1 times 10 to the negative 6 grams. But now I want to get to kilograms. Okay. Well, kilograms is 10 to the power 3. Okay. And so if we want to move up or down this chart, we want to convert again. All you need to do is, once you're at the base unit, you divide by the power it gives you. And so in this case, we're going to divide this number by 10 to the power 3. Or in other words, we're going to subtract the power. So that might be an easier way to think about it. We're going to subtract the power it gives. Okay? So in this case, we're going to subtract 3. And so that we get 9.1 times 10 to the negative 3. All right, my bad, not negative 3. If we subtract it, we get negative 9, right? Minus 6 minus 3. So negative 6 minus 3 is negative 9. And so that's it. This is our kilograms. That's the easiest way to think about it. So first go to your base by the definition it gives you here. So again, micro is negative 6, and so we just have to add that to it, and we're done. And then divide by your next power. I'm trying to get to kilo, so that's 10 to the 3, and so I just divide by that, which is the same thing as moving the decimal to the left 3. It does work going backwards. If we're going like kilograms to grams, or to micrograms, the same thing works. By definition, if we had 9.1 kilograms, that would be the same thing as 9.1 times 10 to the 3 grams, because, again, kilo is defined as 10 to the 3. And then if we want to get to micro, again, you can just divide by 10 to the negative 6. Okay? And then, again, you subtract the exponent in this case, which is minusing a negative 6. So you're essentially adding 6. So we get 9.1 times 10 to the 9 micrograms. And that is correct. 9.1 kilograms is equivalent to 9.1 times 10 to the 9 micrograms. Okay, so that's going backwards. And of course, we get a different result. We get the same number, but the different power because we're going 2 different directions. With that, we can talk about electricity. We're going to be doing a lot of chemistry. Hopefully, a lot of this is a review from your chemistry. or even previous courses. I mean, some of this is going to be like elementary stuff that we've learned, maybe some middle school stuff. So hopefully you know that matter is what stuff is made out of, and matter is made of atoms. That's our main unit source of elements. Everything is made of atoms. Atoms have smaller subatomic particles. They have protons, neutrons, and electrons, okay? We know that protons have a positive charge. We know that neutrons are neutral charged, and they create a nucleus, and they complete the nucleus of the atom. And so because of that, we always know the nucleus of the atom is a positive charge because it has positive charges and neutral charges, which overall is going to be positive, right? Surrounding the nucleus is a cloud where electrons lie, and of course electrons have a negative charge. So the electron cloud, it's the area where the electrons exist. It consists of multiple energy levels, and what you need to know about these energy levels, we're not going to go as deep as maybe you did in chemistry, but you need to know that if we want to move to a higher energy level, that electron has to absorb energy. It needs to gain energy to move from a lower to a higher energy level. And then if we want to go lower energy level, it needs to release energy. Okay. Atoms in charge, so most atoms are neutral charge. So most atoms have an even number of positive charges, They have an even number of positive and negative. They're equal in number of positive and number of negative, okay? Which means they have an equal number of protons and electrons. However, an atom can gain or lose an electron. It's called an ion. Hopefully you've heard of this term before from chemistry. If we gain or lose an electron, we have a positive ion or a negative ion. And so if we lose an electron, we're losing something negative, right? We're getting less negative. Well, less negative means more positive, right? And so we gain a positively charged ion. If we gain electrons, we're gaining more negativity, which means we're getting a negatively charged ion. And so charge is a fundamental unit. It's just a thing. It would be really hard to give you a definition of what charge is, but it's just the base measurement of electrons and this pool between electrons and protons. Okay, so everything has a charge to it. Neutrons are neutral charge, but protons are positive charge, and electrons have a negative charge. And we measure charge in something called coulombs, abbreviated as C. So that's our unit. It's a fundamental unit. Okay. And so it turns out like charges repel and opposite charges attract. You've probably heard of that before, but you need to know if you don't. And so there's a picture to the left that describes that. If you have a proton and an electron, these things are oppositely charged, so they're going to attract each other. Well, protons are going to repel each other, and electrons are going to repel each other. Neutrons, of course, have zero charge. They don't really care. They don't get pulled at all directly. We do need to know the actual charge of the electrons and protons. This is going to be referenced a lot. It's going to be a lot of homework assignments. It's going to be a lot on the test. You need to know that electron has a negative 1.6 times 10 to the negative 16 coulombs charge. Again, we're dealing with a lot of exponents this unit. That's a really small number, and we're going to be dealing with a lot of really small numbers. Protons have a 1.6 times 10 to the negative 19 charge. So they're equal charges, but one's negative, one's positive. Okay, so let's think of an example. An object possessing an excess of 6.8 times 10 to the 6 electrons has what net charge? Well, if we go back, we know that an electron has 1.6 times 10 to the negative 19 charge. So we can take that charge, negative 19, my bad, coulombs charge, and multiply it by the excess electrons we have. And then we can figure out what our net charge is. And so we do 6.8 times 10 to the 6 times 1.6 times 10 to the negative 19. And we should get negative 1.088 times 10 to the negative 12. And if you're using a scientific calculator or a graphing calculator, it might show like 1.088 e to negative 12, of course negative. Of course, hopefully you've seen e before. E just means times 10 to the blank. So in this case, it means times 10 to the negative 12. Okay. So that's what the E stands for in your calculator. An alpha particle consists of 2 protons and 2 neutrons. So what's the charge of an alpha particle? Well, we have 2 protons that are both 1.6 times 10 to the negative 19 charge. So it's 3.6 times 10 to the negative 19 charge. Simple enough. You just need to multiply by how many you have. There's an experiment called the milk and oil drop experiment. This was used to determine the charge of an electron. It's pretty neat. If you'd like to watch the video, you can. It's a pretty cool video. I will not show the video on this lecture though. Conductors and insulators. So these are just terms you need to know. Conductors are materials that allow electrons to move freely. So these are things like metals, gold, copper, aluminum. These are things that you would think of that conduct electricity. So conductors. They have low resistivity. That's why they're conductors. They have low resistance to electrons flowing through them. And then we have insulators. Insulators are materials where electrons cannot move freely. Okay, so like rubber, plastic, glass, they have high resistivity. They really resist electrons trying to flow through them, and so they don't conduct electricity. We also have these things in between called semiconductors. Naturally, they're insulators. So naturally, they don't want to conduct anything, but they can be modified in a way by adding like dopants to them. And if they're added to them, then they will lower their resistivity substantially, and so they can conduct electricity. And so we have a lot of them in our computers in order to do binary for us and in order to be able to turn things on and off in our computer. And so there's a few ways we can conduct electricity. There's a few ways we can transfer electrons from one object to another. We have 2 main terms, conduction and induction. Charging by conduction is if we have a charged object that comes into either a neutral object or maybe an oppositely charged object. The electrons will distribute evenly, so that the charge is the same across both objects. So you can look at the diagram. If we have a negatively charged object and a neutrally charged object, and when they come in contact with each other, those negative ions realize that that neutral object, even though it's neutral, it is less negatively charged than the sphere, right? It's balanced, while that sphere we see is unbalanced. And so those electrons want to move in such a way that they're balanced over both objects. And so they're going to transfer to that other object so that they distribute evenly, so that the charge is the same across both objects. So that's how conduction works. And so if we have a conductor with a net charge of 8 and it's brought into contact of an identical conductor with no net charge, what will be the charge of each conductor when they separate? Well, it's going to distribute evenly, right? So we're going to get a charge of 4C across both conductors since they're identical. If one had more mass, they will distribute the charge like per gram or whatever. But then they might not be exactly 4 and 4. But because we know they're the same mass, it's going to be 4 and 4. We said they're identical. If, again, 2 identical objects have charges -2 and -4 are brought into contact, what will be the resulting charge? So they're going to distribute evenly. So we're going to come to the average. Here the average was between 8 and 0, and so we averaged them, and 4 is the average. Here it's -2 and -4. And so that -4 has too many charges, and so it's going to transfer some charges until they're balanced, until they're both -3 and -3. So -3 is our answer. We have a special kind of charging by conduction. It's called charging by friction. So conduction is anytime we have direct contact with each other. And so charging by friction is when we have 2 objects, they can actually be both neutral. However, one object might have a higher, something called electron affinity. It has a higher, it just means it's more likely to take electrons. It wants the electrons more. Okay, and so in this case, I believe it's the rag that likes to have electrons more. It likes to be more negatively charged. And so when you rub them together, the electrons are able to, they gain a little bit of heat, they gain a little bit of energy or whatever, and they're more likely to bounce, and so they're able to transfer to the item that likes to take electrons. This is what happens when you gain a static electricity from maybe rubbing your socks on the floor or whatever. You're charging by friction, and one of you, either your socks or the ground, normally your socks, they're more likely to gain electrons. And so the electrons hop from the floor to your socks, and then now you are negatively charged, and then now you get such a metal object that wants to gain electrons. It's a conductor, and so That's why you feel a little shock, because the electrons jump from you to the metal real quickly. Lastly, we have something called charging by induction here, and it's kind of complicated, so I threw a GIF in here that you can follow along if you would like to. You can mute me and like run through this slide real quick so that you can see the entire GIF and read its explanations, or you can just pause it as it goes along. But essentially, we have some sort of object that has, a bunch of protons and a bunch of electrons in it, all evenly distributed around the thing. And then I bring a charged object near it. Okay, so let's say it's negatively charged. Well, what happens? Well, the negative repels the negatively charged, the electrons in the object, while the protons are attracted to it. Okay, and not the protons aren't really moving around that much. It's really just the electrons that are moving. Okay, but the electrons are repelled to the other side of the sphere. Okay, then what we can do is we can ground it. Grounding means that we attach something to it that has a large room to gain or lose electrons. And so generally we actually attach it to maybe the ground, like the earth, like rock or the floor or whatever, something that can conduct electricity and has a large mass. And what happens is that because these negative electrons are being pushed to the right side, they actually are some of them are gonna flow down to the ground and balance out. And that's okay, because there's so many atoms here that it doesn't really affect the charge much overall. And so the ground basically stays neutral, even though it's gaining electrons and the charge is changing technically. It's so big that it's not changing a lot. And so those negative electrons are pushed because of that charge. And so now this orb has basically just a proton left, maybe a few electrons left, but mostly just protons. And so then you can take away the charge there, and then now you just have a charged object. So that's charging by induction. And so if you're in class, I'm going to do some demos of this. If you would like to look at these demos, you can look up the silicon rod charging by friction. You can look up an electroscope on YouTube, and you'll see some demos of these kinds of things, charging by induction. Last thing today we're going to talk about is Coulomb's law. So you're supposed to have done a gizmos. Again, the gizmos, this unit are going to be all optional. Okay. But when I say optional, they're highly recommended. They're very, very useful. They're very important to do. I'm making the students in person do them, but they're not for a grade. I'm going to tell them that, but they're not for a grade. But they need to be done, because this unit, it's kind of hard to conceptualize, but if you can get your hands on it, you're going to learn more and you're going to remember more, and you're going to understand it more. And so as much as possible, we want to get your hands on it. We can't get our hands physically on electronics, at least in person. If you're at home, you want to go to a Radio Shack, you can buy yourself a battery and some wires and some basic light bulbs and stuff, and build a circuit out of it. You could even go on Amazon, say like Basic Circuit Builder, and build yourself and order it for like $20 or something, and you can play with circuits at home. But anyways, we have these virtual labs for you that you can get your hands on a little bit. Virtually, I'll get my hands on it. The one today is about Coulomb's law. And so the Coulomb's law is right here. This is a typo. This was supposed to be raised. I think there was an error or something. It should be 9 times 10 to the 9th. So it should be a power there, okay? And so the Coulomb's law says that the electrostatic force, so the force between two charges, we already know that if we had two protons next to each other, they're going to repel each other. Or an electron and proton, they're going to attract each other. Well, that's a force, right? That force is equal to some constant K times the charge of object 1 times the charge of object 2, all over the distance squared. So R is your distance between the two objects. Q is a charge. And then K is just called the Coulomb's constant. It's equal to 9 times 10 to the 9th. If you look it up, it's actually 8.99. You can go ahead and round it in my course. I don't really care. You can round it to 9 times 10 to the 9th. That's what actually I'm going to round it to. But if you really want to be more accurate, you can use 8.99. It's fine. Hopefully you recognize this. That looks awfully close to the gravitational equation. The one that was force of gravity is equal to G m1 m2 all over r squared. They're very similar. It's because they have very similar properties, where g was some constant that we learned then, but we don't need to know anymore. So let's say we have 3 protons are separated from an electron with a distance of 1 times 10 to the negative 6 meters. Find the force between them. Is the force attractive or repulsive? Okay, so we know that the distance, r, is 1 times 10 to the negative 6. We have 2 objects. We have something with 3 protons, and then we have an electron. And so charge 1 is 3 protons. Well, that's 3 times 1.6 times 10 to the negative 19. So 1.6 times 3 is equal to 4.8 times 10 to the negative 19. Charge 2 is an electron, so it's negative 1.6 times 10 to the negative 19. And then we know K already, but I'll go ahead and throw it in here for completeness. K is equal to 9 times 10 to the 9th. So we can go ahead and find the force. The electric force, electrostatic force, is equal to 9 times 10 to the 9th times 4.8 times 10 to the negative 19 times negative 1.6 times 10 to the 19 all over 1 times 10 to the negative 6 squared. And make sure that when you square it, you're squaring the entire thing. Okay? And so very carefully in the calculator. The top, you can just go ahead and throw into the calculator normally. So I'm going to throw in the top here real quick. 9 times 10 to the 9 times, open parentheses, 4.8 times 10 to the negative 19. The parentheses actually aren't important there, but I throw them in anyways because that's what I do. Times negative 1.6 times 10 to the negative 19 divided by, the parentheses here are important, 1 times 10 to the negative 6, close parentheses, and square it, and you should get negative 6.9, 1 times 10 to the negative 16. And I'm going to go ahead and double check my calculator, make sure I typed it in right. 9 times 10 to the 9 times 4.8 times 10 to the negative 19 times negative 1.6 times 10 to the 19 divided by, open parentheses, 1 times 10 to the negative 6 squared. Should be good. That answer looks about right. And this is in newtons. And it looks like a really small number. It is a small number. Well, it's 3 protons and electrons. They're not going to get a lot of force. Let's say 2 charged objects are separated from 1 meter to 3 meters. How does this affect the force between them? So this is a conceptual question, right? We've done these before on the test. And this is actually probably talked about on the gizmos too. And so again, gizmos is good. It's very helpful. Maybe you can already do this if you've seen the gizmos. What's happening here? We're going from 1 meter to 3 meters. That means we are increasing our distance times 3. R is increasing times 3. So what happens if we triple our distance is another way of saying this. Well, let's look at the equation. Our distance is this right here. If we triple that, that means we are putting a 3r in here instead. Okay? And so when you square it, we're getting 9r squared, right? The 3 gets squared and then the r gets squared, so we're left with that. And so we're actually getting 1/9 of the total force, because if we pull out that 9 to the side, it's just 1/9 times all this. And so if we compare this with this, they're the same thing, except for this is 1/9 of our original force. And so this is called, it's the inverse square law is what you can refer to it as. If our distance increases, our force is going to decrease proportionally, but by a square of that number. Okay? So it's going to decrease, so we're going to have 1 over however it's increasing by, but also by the square of that. So the square of 3 is 9, and so we have 1 over 9. If we decreased, so let's say we went from, let's say we went from 2 to 1 instead. So we decreased, we went half. If we're going half, it's the inverse square law. And so we still need to square this thing, but then we need the inverse of it. And so we actually increase by 4. So you bring your distance closer together, you increase your force, which should make sense. You bring those protons and electrons close together, they're going to pull more. They're kind of like magnets. when you bring magnets closer to each other, if they're far apart, they don't really do much, but the closer you bring them together, the more they pull on each other. And when they're really close, they really want to stick together. With that, that's all we're going to cover for today. The homework is mainly some conceptual stuff, some talking about some of the ideas from last time. It's a lot of the conversions, so we just have some raw conversions. I want you to practice those, and then it's a lot of Coulomb's law. That's the most of the worksheet. I want you to do some Coulomb's law. Okay, so with that, you can go ahead and start the homework. Let me know if you have any questions. You guys are always free to email me anything, or Canvas message me, which automatically emails me, so I see them pretty quickly. I'm not always able to respond immediately, but I can respond pretty quickly. Y'all have a good day.